Yeah.
Hello, hello. Hello, everyone. My name is Ken Lazara. I'm the Global Sales Director for CELEROS Flow Technologies, specifically the COPS Vulcan product line, which manufactures valves, control valves, desuperheaters, and steam conditioning valves. Today, we're going to talk about some severe service phenomena used in nuclear power plants and how we solve those problems. So I'm going to turn it over to Pedro to give the initial presentation, and then I'll step back in.
Okay. So thanks, everybody, for coming. Basically, today, we're just going to have 5 topics. We're going to talk about valve basics. We're going to give some definitions of what's cavitation and applications examples, noise application examples, flashing application, and basically close out with that. So it's a brief presentation, but I think it contains a lot of good information, basically valve basics, and how to control processes and make them better in your nuclear applications. So first of all, what is a valve? Right? A valve is something simple. It's been around for thousands of years. First valves used in very simple processes. Obviously now with technology going up to the higher level, which nuclear applications. So in a nuclear facility, you have thousands of valves installed. And what a valve basically does 3 things. So it regulates the flow by adjusting the flow area. Basically, you have a mechanism going up and down, which controls how much fluid goes through the valve. And it basically keeps the pressure, the temperature, the level, the flow within operational parameters. So you want to know, you want to keep it on the control to a certain level. Basically, the control valve is going to do that for you. And then it's going to receive error signals from PLC, DSC to adjust and maintain the process and set points conditions. So basically, that's what you want. You want to make sure that everything happens seamlessly. So you don't want this to be cavitating, making noise, or having flashing. And that's where this type of control valves come in. So that's what we're going to talk about today. So what is a valve just in general? I'm just going to give a few definitions. Not everybody's on the same page. So I just want to introduce what a valve is. So you have basically in our lines, you have several types, but these are 2 of them that we use typically in a nuclear application. And the valve has the body. You have the bonnet, which is the top portion. You have an actuator, and you have a controller. But what the heart of the valve is basically what's inside of it, which is the trim. The trim set is basically what controls how you're going to regulate the fluid, right? How much CV you have, what is the percent open, et cetera. So you want to make sure that you select the good trim for the required application. And within the application, you have many different ones. So you have from the very basic to the very complex, right? And each one will solve different problems to the different processes. And within the trim set, you have a seat, you have a plug, you have a cage, you have a stem, and basically each one of those trims will have a different CV characteristic. And the CV is basically what you want to control. You want to see basically how much flow you want to pass through the valve at a certain opening, and that is going to be regulated by the flow, by the trim itself. And then within the trims, you want to make sure that you don't want to have noise, you don't have cavitation, you don't want to have flashing. And depending on your condition, the pressure drop, the temperature, you will have to select different type of trims. So as I was saying, you can go from the very basic, you can go to the very sophisticated ones, and the very sophisticated ones can be used for almost any application out there in the market. Okay, and just basically where the valve is used, basically you have several types of reactors used on a BWR, boiling water reactor. You have different conditions, and this is what's important to us, right? You have the steam line operating about 287 centigrade with a flow rate. So depending on the flow rate and the temperature, that's where you're going to have to select the type of valve, the size of the valve, the trim type, et cetera, basically to be able to regulate that flow. And basically, you have here, these are the symbols for valves. And as you can see, you have on the main water, feed water line, also on the steam line. So this one is low temperature. This is high temperature. And about 10% of the 13% of the reactors today are boiler water reactors. Those are first-generation reactors. And as you know, there are a lot of those being expanded, being adapted, and that's where we come in. So basically, you have an old application where you want to expand how much fluid you pass through the valve so you can make your plant more efficient. That's where the train comes in. And then you also have the power boiler reactor, pressurized water reactor, and about 70% of nuclear reactors today fall into this category. And the same of this, you can see here the conditions are similar and the pressure and temperature, right? But the difference here is that you have the main containment, you have basically all the valves will be located here, most of the valves. And we and CELEROS, we do the two types, so basically inside of the reactor, outside of the reactor. And as I was saying, basically, depending on the application, you will select your valve. So with that said, I'm just going to pass it up to my colleagues to start talking about examples.
Okay, thank you. Thank you, Pedro. So today we're going to talk about some best practices, whether it's an existing nuclear power plant, whether you're upgrading or doing a life extension, or whether it's a new power plant. So we're going to give some real life examples in certain applications. First off, we have a couple of definitions. You know, you got the Brunelli principle that basically says as velocity increases, pressure decreases, right? In any valve, you have the vena contractor. The vena contractor is the place where the orifice is the smallest. So you have the highest velocity and the lowest pressure. These are all very important. Then you have the vapor pressure. Okay? If you have a liquid going through a line and that liquid drops below the vapor pressure, okay, it's going to turn into a vapor or turn into a two-phase flow where you have both water and steam or a gas and a liquid in that particular application. So let's talk about some particular ones. Let's give a cavitation example. So this is what I was meaning about cavitation. In this particular case, you have the pressure, the inlet pressure, with a big pressure drop dropping below the vapor pressure line, okay? And then it's recovering. And as it recovers, there's certain vapor bubbles that form. And as those vapor bubbles form and it recovers, those vapor bubbles implode. And when it implodes, it impinges upon the material and will cause severe service damage. It will damage that trim and can damage pipeline if you have cavitation in the pipeline. Pumps have cavitation, okay? So let's talk about a specific application. This is MSRs, a moisture separator reheater, all right? MSR is unique in a PWR type plant because basically you have the reactor, it's going to the steam generator, which is producing the steam. That steam goes directly to the HP turbine. Now, the exhaust from that HP turbine goes into the MSR, all right? The steam in that HP turbine is expanding, and once it expands, it's losing its energy, and there may be moisture in the steam. Why it goes to the MSR, okay? The MSR purpose is to separate the steam from the moisture, reheat that steam, and then send it back into the LP turbine, right? You want the most efficient steam going back into that LP turbine. So, in this case, you need a control valve to handle the water. Where's the water going, right? So you have the HP turbine going into the MSR. It's separating steam. The steam, now that's been reheated, is going into the LP turbine. The water that's separated is going back into the deaerator. All right, so you need that because you need to control the deaerator. It's a sensitive piece of equipment. You know, it has certain pressure requirements, so you do not want to overpressurize your deaerator. So you have this valve in place to send that water to the deaerator. The problem with that is, and I'll give some examples, and this is a perfect example of best practice. The problem with that is it's a cavitating application, okay? And we have lots of examples when existing nuclear power plants were built, okay? And I guess this is one of my best practices, to always give all the proper conditions. As you can see, when we initially did the sizing on this valve probably 30 years ago, we were only given one condition for the valve, and that condition wasn't cavitating. So then we got a customer saying, hey, this trim's getting damaged all the time. This trim's getting damaged all the time. We pull out the spec sheets, we look at it, we evaluate it. We're saying we must not have all the conditions. They do an analysis of the plant. They realize, oh, these are the true conditions we're working through. These 3 conditions, and 2 of the ones that they didn't give us initially are cavitating. Okay, so that's a very key, whether you're building a new power plant or, you know, upgrading plants, to understand all the proper conditions the valve needs to operate under. Okay. Damage from cavitation is very severe, okay? That impingement, I don't care what material you make it out of. You can make it out of the hardest material. You can make it out of stellite, unobtainium, whatever you want to come up with, cavitation is going to damage it, okay? If you look, it's interesting because when I have a valve problem in the field or somebody comes, I can typically tell by looking at the trim. If you look at this trim, this is the implosions of those bubbles, so you can see it's a very rough surface from where that cavitation impinged on that trim. Okay? So, how do you solve this? How you solve this is you need a special trim. Pedro talked about the trim being the motor and everything else. When you have a trim that has several stages like this, instead of taking the pressure drop in one drop going below the vapor pressure, okay, you come up with a trim that slowly drops that vapor pressure going through these stages and going through it. So you go through a stage, you go through a stage, you go through a stage, and that pressure never drops below the vapor pressure. All right? Basically, you are capable of eliminating any cavitation in a control valve, okay, with the proper trim. And there's lots of different types of trims for this application, for different types of application. Okay. You know, the MSR needs very tight shutoff also, so we have a class 5 valve here. And this is just an example where I showed you the prior slide where it had cavitation. Putting the proper trim in, the cavitation is now gone. Okay. Let's look at one more cavitation example. Okay. This is a condensate recirculation valve. First off, almost all recirculation valves in a plant, okay, cavitate. All right. The recirculation valve in most cases is meant to give minimum flow back to the pump. You need at least 30% of flow going always recirculating back to the pump, or you're going to damage the pump. Okay. So in this case, you have the MSR. We talked about the MSR. We talked about the exhaust after it goes from the MSR. It goes into the steam goes into the LP turbine after it's been reheated. In this case, it's going from the LP turbine. Now, where does that exhaust go? It goes into the condenser. The condenser is condensing the steam back into a liquid, getting pulled through the condensate pump, sending it to some low-pressure heaters, and then sending it to the deaerator. But when that deaerator doesn't need anymore or cannot handle it, or when something's not operating, you must recirculate that pressure or that fluid back through the pump. So in this case, we're just trying to show you that this is a valve size without cavitation control trim, so you can see it's cavitating. But in this case, the customer had another unique problem, which is common in older plants, whether it be a nuclear plant, whether it be a coal plant, whether it be a gas-fired plant, that he had impurities in the system. You see this a lot in the boiler feed water recirc systems. You see that in the condensate systems. That ends up with magnite, other type of impurities in the system. Those impurities either clog when you have cavitation control trim. Remember, you have stages, so you have smaller holes, so it either clogs that or it's damaging the seat. If that impurity gets on that metal seat, it will damage it as the valve plug is closing and trying to close on it. So in this case, the customer wanted very, very tight shutoff, okay? He wanted a solution for his impurities. So what we were able to do was design a very specific trim, and this is great for all recirculation valves, that included a strainer at the bottom to strain out any of the impurities. Any small impurities that made it through the strainer, we put in a soft seat, but this isn't just any soft seat, it's a peak seat, okay? And these impurities, what's interesting, if anything makes it through the strainer, it actually will get embedded into the peak seat and still maintain the tight shutoff. Okay. So again, we provided a nested cylinder cage, that tight shutoff, the soft seat for the tight shutoff, the strainer to remove impurities, and solve the problem for a customer. These are all things you should be considering on new applications, on upgrades. Are you using the right valve for the right application? Let's give an example about noise. What causes noise? Typically noise is some type of gas, steam, going through a pipeline at super high velocity, right? You know, it propagates, it makes sound, and then that sound will propagate downstream. I've seen downstream equipment from noise being shooken so bad that basically parts were falling apart, welds were breaking. Typically, anything over 100 dB is damaging. It's going to damage the valve, going to damage other equipment in the plant. Got to be very, you know, conscious of the noise. In this case, it's interesting. You know, there's certain solutions. One is you want to keep the speed of that gas below 0.3 Mach. Very simple, okay? You could increase the outlet pressure so you don't have that velocity going down. Yep, you there? Okay. You could add a second valve. That's another cost. That way you're taking the pressure drop or the velocity across two valves instead of one. And you could increase the insulation, right? We all know on a valve, they add insulation on steam lines or gas lines, all right? But that does not solve the problem of the noise being damaging by adding it. It just makes it quieter. Okay. So let me talk about another application in a PWR plant. This is basically the main steam to the MSR heater coils. I tried to keep it around the same application. So we got the moisture separator reheater. We talked about the reactor sends heat to the steam generator. It creates steam. It goes to the HP turbine, goes into the MSR. We talked already about the liquid from the MSR going to the deaerator. Well, the steam, okay, is then going to the LP turbine. How do you reheat the steam? Typically, you're reheating that steam by taking off the turbine header and taking the steam off a turbine header and running that down to the MSR, and that's how you reheat the steam in the MSR, okay? Now, you need a control valve in this application because you can have a lot of noise, you have a lot of velocity, you need to control that steam going back to the MSR. I'm just giving two examples. In this case, let me just go back. In this case, did I show that? In this case, we actually used our special trim, okay, to reduce the velocity called our Raven trim, which is a disc stack trim, has several different stages. It could be customized for any particular application, okay? But I'm just trying to give an example here is I size this valve without using the noise trim, okay? And then I sized it with the noise trim, with the Raven. You can see this was up at 113 dB. But my first reaction was this plant really wasn't designed properly for the application. Because if you look at this, this thing was an 8-inch valve line going to the MSR. So that 8-inch valve line, and you're seeing 750,000 pounds per hour of flow, which, my goodness, you know, should probably be in a 12, 16-inch valve line. So wrong valve solved, but wrong pipeline selected initially, but we can still solve that problem, as you can see by making that noise go down to 90, 85 dB. The last example I'm going to give is flashing, okay? Flashing is very similar to cavitation. You have a pressure drop, and it goes below the vapor pressure line. The only difference is it can't recover. And there's no valve in the world that can make that vapor recover above the vapor pressure line. That is a system problem. Typically, it may be a drain line going into a condenser where you have vacuum. But no matter what, you can put velocity control trim in there and try to make the severity of the flashing less, but you're going to have flashing, which is basically typically a two-phase flow. So you have a liquid going through, it's flashing off, it then becomes a mixture of, you know, steam or whatever the gas is and water. Okay? So flashing damage is just the opposite of cavitation damage if you look at this. Flashing damage is leaving smooth surfaces, typically but it's very erosive. As that two-phase flows flashes, it is just cutting away the trim versus pitting it in the cavitation example that I showed. Okay? So I mentioned that you cannot solve flashing, but there is some best practice, and it's amazing how many globe valves or how many times I've seen flashing applications where when it's flashing, let me go back to that picture real quick. This is an example of a globe valve. It's flashing. It blew out the bottom of the body, right? Because that flashing is just going to keep eating the bottom of that valve body until it's going to keep eroding it, and it's just going to be gone. And next thing you know, you got high pressure steam coming out the bottom of the body. So what can we do? Well, globe valves is basically the flashings in the direct area of the flashing. So in all cases, you want to, when possible, use an angle valve for any flashing application. Okay? Velocity trim, as I mentioned, can reduce it, can reduce the severity, but it's going to flash anyway. All right? You can use hardened trim. You can put weld blobs on the bottom of the body. So the other thing, when you're turning from this liquid to the two-phase flow, remember, as as a liquid turns into the gas, it's expanding. Okay, where's it going? Where's that expansion going? If you don't have a bigger or a larger outlet on the valve, then basically you're choking the flow. When you start choking the flow, you have a problem controlling that whole system because it's just clogged up there. Okay? What we can do is we can design trim that basically directs the two-phase flow to an area of lower velocity. Whether that's an angle, the ideal situation is you put an angle in here. This is going to flash, all right? I'm going to put some special long seat ring here that takes that flashing away from that valve and blows it into the pipeline. Over time, that pipeline is going to have a problem, but you're going to protect the valve, okay? The same thing can be done with a globe valve. We can put a baffle-type trim to send it towards the outlet instead of straight down into the body where it damages things. Okay? So here's a couple of examples of flashing that I just found where we put in trim that directed the flow away from it, because these were both, for example, this is a globe valve. The positive, it's a 4-inch valve, it's got an 8-inch outlet. So at least when it flashes, it's got somewhere to go. We put a baffle trim in here to direct that flash away from into the outlet, away from the valve body. In this example, this is, you got some velocity control trim here, but the outlet size is the same as the valve. So best practice, you want to use an angle valve, you want a larger outlet, and you want some type of directional control trim inside the valve. So just to summarize it, we didn't have a lot of time to go over a lot of material. We'll be next door if you have any questions. Building a plant, have old plants with problems, we can solve it. But listen, always provide all the application conditions. You can't believe how many applications when I pull up, when I talk to customers, we installed valves in plants 30, 40 years ago. You can't believe how many of these have one condition, two conditions for an application, like a research application that is they're seeing 4 or 5 different applications, 4 or 5 different conditions. Okay? If cavitation is present, always use cavitation control trim. All right? Flashing cannot be eliminated. If you see flashing or if there's flashing in an application, you want to try to use an angle valve where possible. You want to use a larger outlet on the valve. When noise is present, verify the pipe size and trim are appropriate. Do not try, sometimes people cut corners and say, oh man, I can do this in an 8-inch pipe instead of a 10-inch pipe. You're just going to end up with problems down the road when you do things like that. And I guess the last thing I'd say is control valves are very versatile, right? Pedro showed you how many different types of trims there are that can control cavitation, control flashing, control noise. I see a lot of new, I guess spec sheets for new build SMRs and other plants. I see a lot of applications being changed to on-off valves. You know, and I get it, on-off valves are cheaper, and it's very appropriate in a lot of conditions, in a lot of applications that an on-off valve be applied. But I think if you have some of these severe service type phenomena that I talked about today, even if it's an on-off application, only a control valve can offer you the versatility and trim selection to control all these severe service phenomena that you see in power plants today. Okay? So, saying that, we're CELEROS Flow Technologies. We got 60 plus years in the business. We manufacture nuclear pumps and valves. We have thousands of coated valves installed in all over the place, 50 plus nuclear applications. 65% of all nuclear power plants around the globe have our products installed, and we have 4 accredited facilities globally. So, have any questions, you know, today, in the future, about valves? You're not sure about something? Feel free to reach out to me. We're going to be next door. You can talk to me here, and thank you for your time. I really appreciate it.